Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Hello everyone. My name is Wei, and I'm the dev leader of Kinect for Windows China team. And today I will give a brief introduction about the Kinect for Windows SDK. And here is today's agenda. We will talk about the hardware first, and then give an overview about the SDK architecture. And then we will go through the depth, color, and skeleton stream one by one. And in the next, we will talk about the advanced topics such as how to sync streams and how to mapping between each coordinate space. And if we have time, we will cover two major features provided by the Kinect toolkit, named Fusion and Interaction. Okay. Now let's look at the Kinect hardware. Well, this is a real Kinect hardware. And this diagram shows the major components of Kinect hardware. As we can see, the IR emitter, this one, IR emitter, will emit the infrared light to the object. And the IR depth sensor, actually this one, is IR depth sensor, will receive the reflected light from the object and calculate the depth data based on it. And the color sensor will capture RGB image. And the tilt motor will control the tilt angle of our Kinect. Kinect also has a 4-element microphone array, which could provide the high-quality audio stream. We also have the accelerometer. The accelerometer could be used to detect current Kinect port if it is placed normally or to bottom up. Kinect camera has a view angle. It's 43.5 plus and minus 27 degrees in vertical, and has a fixed view angle of 57.5 degrees in horizontal. Our Kinect sensor provides the following raw data streams: the color stream, depth stream, and the audio stream. We also have the infrared stream and the accelerometer stream. And based on the raw data streams, Kinect for Windows SDK provides the following three recognition streams. Skeleton tracking stream will only use the depth stream and track the player's skeleton. Speech recognition stream was built on the audio stream. And the feature tracking stream used the color, depth, and the skeleton stream together. Okay. Those are basically the hardware overview about the Kinect. Let's see our Kinect for Windows SDK. To install Kinect for Windows SDK, we only need two simple steps. The first one, we must unplug our Kinect sensor and close the video studio. Then we can download and install the Kinect for Windows SDK and the toolkit from this URL. Okay, now let's look at our Kinect for Windows SDK architecture. This picture shows the major class in our Kinect for Windows SDK. And the Kinect sensor, this class, is the entry point for all Kinect-related functions. The static variable Kinect sensors keeps all the Kinect sensor instances currently connected to our system. The depth stream, this one, keeps reference to a depth image stream class. And the depth image stream class encapsulate all the operations and the properties related to the stream. This is depth image stream class. As we can see, the enable method in the depth stream could be used to enable the stream. And also, we can get the next frame by just call the open next method. The depth image stream also provide the properties such as format or min-max depth. Color image stream is very similar to the depth image stream, so we will just skip it. Scale stream is a little bit different. Besides the enable method, we also have the disable method. That means our scale stream could be disabled because they are calculated by our Kinect for Windows SDK, not provided by the hardware. We also have the truth skeleton method in our skeleton stream. Truth skeleton method could be used to choose the skeleton data we want to get in next skeleton frame, and we will talk about that later. Okay, this is all the major class in our Kinect for Windows SDK. And we have two ways to retrieve a new frame from. The first is the pulling mode. We can just call the open next frame method, which was in each stream class, such as the depth image stream, or color image stream, or the skeleton image stream class. We can pull a frame out, or we can register an event handler. Color frame ready event, depth frame ready, and the skeleton frame ready events are provided by the Kinect sensor class, as we can see from this picture. This is the depth frame ready event, color image, and the skeleton frame ready event. When the new frame is ready, this event will be triggered. So our register event handler will be called, and the frame will be passed by the event argument. So it's a two mode to get a new frame. First one is the pulling mode, the other is the event mode. This is the general design principle in our Kinect for Windows SDK, and almost each data stream are provided with two modes. Any question? Okay. Now let's look at the depth stream. Depth stream is a great invention because it enables our computer has a 3D vision. And the depth stream consists of a series of depth frames in order of time. And each depth frame contains the depth pixels. In each depth pixel, we have the distance information from the object to the sensor plane. As we already mentioned, the depth stream was calculated based on the IR emitter and the IR camera. IR emitter will emit infrared light with a certain pattern, such as a lot of red dots. And when the light reflects from the object, the pattern will be changed. And our Kinect sensor will capture the reflect light by our IR camera and calculate the depth data based on the changed pattern. So this is the depth measure pattern currently we use in our Kinect 1.0. In 2.0, it's a totally different technology. The depth sensor has two depth range. Default range with reliable depth from 0.8 to 4 meters. And in near range with reliable depth from 0.4 to 3 meters. Beyond this range, the depth data could either be too far, too near, or unknown, as we can see from this picture. Our Kinect for Windows SDK supports 3 depth frame formats. Actually, hardware only provides the second format, but our software uses interpolation to produce a more higher resolution format for us. Okay, this is all the basic concepts about the depth stream. Now let's look at how to get the depth data by code. First thing first, we need to install our Kinect for Windows SDK and toolkit. Online, we only need 4 steps to get the depth data. The first one is to find an available sensor, then enable depth data stream, and then register a stream ready event handler, which could be used to receive the new depth stream, and then we start capturing data. Let's look at the 4 steps one by one. Now, this is the first step. As we already mentioned, Kinect sensor has a static variable named Kinect sensors. It keeps all the records for all the Kinects currently connected to the system. So we can enumerate all the sensors in our system, and then find if any sensor status is to connected. That means the sensor could be used by us. So we can take this sensor and break this enumeration process. So besides the connected status, our Kinect sensor also has the other 3 status. Disconnected means that the sensor was unplugged from the USB port. And initializing means that the sensor is being initialized. And not powered means that the sensor is plugged into the USB port, but the power line is disconnected. Okay. So the connected status means that the sensor is off visible. Now the next step is to enable the depth stream. We only need one line of code. That's called the enable method in the depth stream class, and pass in a depth image format parameter. Then we need to register an event handler to receive the new frames. Also, we only need one line of code. At last, we will start a session to capture the depth image data. Okay. After a new frame is ready, our event handler method will be called. So in the event handler, we can open our depth frame by calling the open depth image frame method provided in the event argument parameter. And if the depth frame is not null, means that it's a valid depth frame, so we can copy the data out. And in each depth pixel, in the depth frame, there are 2 kinds of important information. One is the depth. It's the distance in millimeters between the sensor plane to the object. The other is the plane index. If Kinect for Windows SDK detects a plane in the depth data, it will assign a plane index for each pixel of this belong to this player. And the Kinect for Windows SDK can track 6 players at max, so the play index will be from 1 to 6. And the play index 0 means that this pixel doesn't belong to any player. Now let's see how to get depth data by code. This is the sample code. As well, we'll do all the works, all the initializing works in our Windows load measure. So first one, we will find the available session. In the line, if we find the session, we will enable the depth stream. And line allocate buffer to store the depth pixels. Register an event handler to receive the new depth frames. And at last, we will start the session. In the event handler, we will open the new depth frame and copy the pixel out and line display on the screen. So let's see what's the result if we run this application. By the way, this is the toolkit user interface. All the samples are based on the toolkit browser, so we can download or just directly run the sample from the toolkit. Let's find our depth frame, depth basic sample. Basic. Oh, sorry. It's displayed on my screen. D. No? It's stored here. Well, this is depth data captured by this sensor. Okay. And we also have the new mode, as we just talked before. We check new mode, so it will not be visible because, now. Yeah, you are just on the boundary. Okay, any questions? No? Okay. Now, let's look at the color data. Color stream also consists of frames in order of time. And each color frame consists of pixels, its color information or the brightness information. Kinect for Windows SDK provides 3 types of color frame. We have 3 resolutions for RGB frame, and 1 resolution for IR frame, and 2 resolution for Bayer frame. So this is the 3 types of color frames. Now let's see how to get the color data. Now it's very simple and very similar as how to get the depth data. We also need 4 steps. First one, find the available sensor and enable the color data stream. That is the color event handler, and then start capturing the data. You go through it. Find the available sensor and enable the color stream. To enable color stream, we just need to call the enable method, which is located in the color stream image class. And register as event handler to the color frame ready event, which is located in the Kinect sensor class. Now we start the sensor to capture the color image data. Well, the event handler method is quite similar with the depth one. We can get our color image frame out by called the open color image frame method, which is provided by the color image frame ready event args, and copy the color image frame pixel out and calling this method. Now let's talk about the skeleton data. Skeleton data consists of 20 joints position of human body. So this is the skeleton, and this is the skeleton. And our Kinect for Windows SDK can recognize up to 6 players, but can only give full skeleton of 2 of them, because due to the performance limitation, so we can only calculate the 2 skeletons. And the skeleton data is also organized in stream of frames. And each skeleton frame is based on the calculation of depth frame. And each skeleton frame contains up to the 6 skeleton data structure. Before trying to get the skeleton data by writing code, let's talk about several basic concepts about the skeleton data. The first one is the tracking state. A tracked player can either have the tracking state track or position only. A tracked skeleton means that we will have all the details about each joint of the skeleton. And the position only means that we only give the hip center position, the information of the hip center joint. So no detailed information for each joint. And this picture shows all the skeletons that we can provide by our Kinect for Windows SDK. Basically, they are organized in a tree. And the hip center is the root of the tree. And the hand right, hand left, foot right, foot left, and head is the leaf of the tree. So this is the 20 joints we can get from our Kinect for Windows SDK. We also have 2 tracking modes. The default mode, we can track all the 20 joints. It's optimized for the fully viewed player. And the sit mode, we only track the 10 joints of the upper body. It's optimized for the sit player, whose lower body is not fully visible. And we also have the concept named the active user tracking. As we just know that we can track 6 players at the same time, but we can get the skeleton data for 2 of them. So Kinect introduced the mechanism named the active user tracking, which can make our application look like they are tracking the 6 skeletons at the same time. So to implement this, we just need to call the choose skeleton method when we get a skeleton frame. This method will specify what's the next 2 skeletons we want to get in next skeleton frame. For example, if we have 6 players, 1 to 6, and in frame 1, we get the skeleton data of player 1 and 2. And then we will ask our Kinect for Windows SDK, give us player 3 and 4 skeleton data in next frame, and player 5 and 6 skeleton data in next frame. So, since our skeleton stream is it's about 3 frames per second, that means we can get 10 times of a user's skeleton data in 1 second. So it make our application look like they are tracking all the 6 players at the same time. Am I clear? Okay, now let's see how to get the skeleton data. Install SDK, and also have very similar 4 steps. Find the available sensor, enable the skeleton stream. This method doesn't have any parameter because we have no choice, only one type of skeleton frame we can get. And register an event handler. and then start the session to capture the skeleton data. When our frame-ready event handler was called, we can get the skeleton data by calling this method. And then copy the skeleton data out. Now let's see a demo about the skeleton data. So let's open our toolkit browser. Find the one named skeleton basics. Click run it. Nothing happened because no skeleton at the front of the session. Let me see. Here is mine. See, it's 20 joints. All joints we can get. Okay. And as we already mentioned, there's a seed mode. So if we check this box, now only the tangent of the upper body will check. So it is optimized for the seat players. Now, in each skeleton data class, we have following information. We have the tracking ID of current skeleton and the position information. Also, we have the tracking state to identify if the 20 joints are checked or only the position of the hip center provided. We also have the clipped edge. And the bone orientation is a collection of bone orientation structure. In each bone orientation structure, we have the start and the end joint of this bone. And also we have a rotation matrix and vector related to the camera or the parent bone. So we can get even information about the current body pose, such as if it's this or like this. We also have the collection of joints. In each joint, we have joint type, position, and the joint tracking state. And each joint can have tracked, not tracked, or inferred state. What is the inferred state? Let me see the demo again. If the joint is tracked, it will be a green line. But sometimes, maybe for example, my leg, sometimes the joint is not tracked. It is not visible. But we can infer that the joint should be at this location, so it's the inferred joint. So we can calculate based on some common sense that the arm should just like this length, never be 3 meters. Okay, and that's all about the skeleton data. Very quick demo. So, any questions? Okay, let's go on. Now let's talk about several advanced topics which we may use in our application. The first one is how to synchronize among different streams. We have color stream, depth stream, and skeleton stream. Sometimes our application may need to use both streams at the same time. So our Kinect for Windows SDK provides an event named All Frame Ready. This event will be triggered if we get a color, depth, and a skeleton stream at the same time. And the timestamp property in each frame will record the real creation time for the stream, for each frame, sorry. Okay. And now let's see coordinate mapping. In Kinect for Windows SDK, we have 3 different coordinate space: color space, depth space, and skeleton space. Color space and depth space are 2D space. The X value goes from left to right, and the Y value goes from top to bottom. And the pixel in color space is the RGB, or the brightness information. And the pixel value for depth space is the depth information from the set plane to the object. Skeleton space is a little bit different. Skeleton space is a 3D space. And as we can see from this picture, the skeleton space is a right-handed coordinate system. What is a right-handed coordinate system? I think this is my right hand. This is the y-axis, and this is the z-axis, and this is the x-axis. So the origin is at the center of the sky our sensor. So this is the origin, and this is the y-axis. This is the z-axis, and this is the x-axis. So x-axis was extended to the left, and the y-axis extended towards up. So yeah, it's shown in this picture. To map a point between those coordinate space, we can use following several methods provided in the coordinate mapper class, such as we can map a color frame to a depth frame, or map a depth point to a color point, or map a skeleton point to a depth point, such as. So now we talk about the accelerometer. The accelerometer vector is a 3D vector pointing in the direction of gravity. So it's always pointing in this direction. And the vector is in gravity unit. We can get the accelerometer by calling the accelerometer get current reading method provided in our Kinect sensor. And the return value is the vector form data structure, and the W value in this structure is always be set to 0. Only X, Y, and Z has the real value. And the vector also is a right-handed system, same thing as the skeleton's coordinate space. So from the picture, we can see what we will get if we call this method. If our Kinect sensor was placed at this board, and this is the x-axis, right? And the y-axis and the z-axis. So the gravity direction is in this direction, right? So the x value will be 0, because the x-axis perpendicular to the gravity direction. And the z value is also 0 because they perpendicular to the gravity direction as well. And the y-axis will have a minus 1g because they are in the outside of the direction. And if we change our Kinect in this pose, now this is the x-axis, and this is the y-axis, and this is the z-axis. And the y and z will perpendicular to the gravity direction, and the x-axis will have the value of 1. Am I clear? Okay. If I am clear, I want to ask a question. What happens if I change the Kinect pose on this side? So, like this pose. What's the x and y and z value? Can anyone tell me? Can anyone tell me?
Minus 1, 0, 0.
Correct?
Minus 1, 0, 0.
Yes. Minus 1, 0, 0. Because, yes. Because y and z also perpendicular to the gravity direction. And x should be minus 1. Okay. That's all about the basic concepts of Kinect for Windows SDK. Sorry.
I have a question. Does it also allow blocking point position?
Yes.
To change the angle?
Yes, they allow it. Actually, it's a dot product with the gravity direction.
Okay.
And the unit is in the gravity unit G. Okay. Now, we have covered all the basic concepts about the Kinect Fusion SDK. Now let's talk about Toolkit. Toolkit includes a lot of samples and several very important libraries which provided by Kinect for Windows Toolkit team. Actually, I'm working on the Kinect for Windows Toolkit team. The first one is the Kinect Fusion. Kinect Fusion provides 3D model scanning and model creation functions. The highlight of Kinect Fusion is that it's a real-time 3D model reconstruction library. Real-time 3D construction library. And the model could be exported as a STL or OBJ file used by third-party applications. Now, before talking about the technical detail, I want to show a demo about Kinect Fusion. It's hard to find one more pointer. So that Kinect Fusion actually need a powerful graphic card, but my laptop has not such a powerful graphic card, so the performance is not very good. As we can see, when we and the reset the reconstruction. So can you just stand Inside the reconstruction. Now it's a 3D modeling. Yeah, start. Actually, when rolling the camera, we can build a fully 3D model of the store. And the performance is not very good. Sorry about it because my computer is not such an expensive graphics card. Okay, this is the basic example about Kinect Fusion. Let me open another sample. It's too big for this screen. Oh, it's too big for this screen. I cannot operate. So let's just ignore this sample because it's too big.
Afterwards.
Yes. If anyone are interested, come here after the tutorial. Okay, let's now talk about how to use our Kinect Fusion library. First, we need some environment setup. Of course, we need to install our Kinect for Windows SDK and toolkit. And we also need a DirectX 11 graphic card and a DirectX 11 installed in our system. Kinect Fusion library supports C++ and C# programming interface. Now let's talk about the Kinect Fusion architecture first. I'll list the overview about the Kinect Fusion library. Fusion depth processor. It's a static class, and all the methods in this class are also static. Basically, they are versatile to APIs and provide the basic support to build a 3D model with or without use the reconstruction class. And the reconstruct class is the most important class in our Kinect Fusion library. There's a method named the Fusion Create Reconstruction. It's a factory method. We will use this method to create an instance of our reconstruction class. And our reconstruct class holds reference to a current volume we have built and the current camera port. Let's talk about some behind the principles first. To build a fusion, to build a 3D modeling. To build a 3D modeling, Kinect Fusion uses an equation operator. For example, if our 3D modeling is like this, and in our system we already have a volume builder like this, and our finger is the common part. For the new input depth stream, we got a model like this. The finger is a common part of our 3D model. So in Fusion, we use iteration operator try to align the new input depth stream with the volume already we have. So maybe the intuition algorithm will try several times and got an alignment. Then we will get a camera pose above the current volume, because the volume was like this, right? And the new depth frame, like this, after alignment, we got a new camera pose. So based on the new camera pose, we can integrate the new input depth frame for our volume. I'm not sure I'm very clear about it. Okay. I'm clear. Sorry about it. Let me repeat it again. For example, this is the volume. This is the volume already we already built. And this is the camera. This is the current camera pose for this volume. If we get if the whole 3D model was like this, as a circle. So maybe we need for a new input depth frame. Let me call it. But for the new input depth frame, maybe it's hard to describe actually. Sorry. Maybe. Let me start from the beginning. At the beginning, our fusion library has an empty volume and an initial camera pose. So maybe just the camera pose within the original of our coordinate system. And then we get a depth frame. So this depth, we will build a 3D model based on this depth frame. For example, if the depth frame was cover this part of the 3D model, then we'll get a frame, right? And the camera pose will not change. Then we get the second depth frame. For the second depth frame, we may get a depth. We may get intuition about this part of the 3D model. So there are some common parts of the depth model and the depth frame. So we will use this algorithm to align the common part. After we get align the common part, now we can find that we have seen this part are new for our 3D model. So the camera must change so we can observe the new part of that model. Okay. So we will get a new camera pose, and we can use this camera pose to increase our volume. Okay, I'm clear. Okay, and this is the fusion pipeline. When we get the new depth frame, we need to convert it to the depth plot frame. Because our fusion only accepts the depth plot frame of the depth format. And we have two choices to integrate this frame. The first one is called the process frame. And the second one is called the align depth plot frame to be constant and the integrated frame. Process frame basically implement the same functions as these two methods did. But this method will do all the work on GPU. So the temporary result will not need to copy from GPU to CPU memory. So it saves a lot of time. By calling these two methods one by one, we can get more fun and control of the 3D model. After we got the 3D model, we can use the factory point cloud or factory map to get the 3D model out. By calling the factory point map, factory map, we can get a nice class. This class will basically the 3D model. It's all about the fusion. Any questions?
I'd like to make a comment about Fusion. Fusion is, there's a lot of innovations that are happening around the context of Kinect. This has specifically come out of Microsoft researchers' work. There was some significant research that was published at SIGGRAPH this year in August that is further expanding the capabilities of this technology, so that you can now build very large models of very large spaces, not just a room space, very quickly. And then if you look at what's going to be published at SIGGRAPH Asia in the next couple of months, there'll be more research published. So this is on the bleeding edge of what's coming out of the research in Microsoft. And it's getting very quickly transferred into the product here. So straight from research papers into product technology that is available commercially now for people to use. And it's very, very bleeding edge technology. And the neat thing about it is it's working in real time, and it's very, very quick. You can build 3D models slowly using the other technologies, but this is very quick.
Yeah. And also in the
With a fast GPU.
Yes, fixed fast GPU. And also in the latest fusion release, we support the color information in after the 3D model. So in the future, maybe we can get a real person, the 3D model of a real person with the color in.
It looks better with silver speed.
Okay. Okay, now let's talk about the interaction stream. Okay, before we talk about the interaction stream, let's see a demo about it. Interactive stream provide the easy way for the developer to get a Kinect enable control. For example, actually our interactive stream will also provide several visual controls. That's the last So I can use my hand to push the button. Now on the scroll button. My hand to the grip stick. I can grip the button and drop. So this is the interaction controller provided. Before looking at code or the library, let's talk about the physical concept first. The first concept is physical interaction tool. Basically, the physical interaction tool is a tube around the left shoulder and the right shoulder. almost around the base this area, as you can see from this picture. And we also define all hand gestures, release, this is release, and the pricing and price. We also had a hand gesture need to break. Release, pricing, price, and break. Now we have a concept in the price attraction point. Only trying to press a button by hand is hard to press because only pressing on target our hand is also moving. So to make sure the user can easily press on button, we need to use the press attraction point concept. When we trying to press on a UI target, Kinect library over time will query from the visual what is the attraction point it is. And it will adopt our hand position towards the attraction point. So it will make us very easy to press on the target, press on the target. And we see the demo. This is button. Only pricing. I'm not sure if you already got it. Only pricing, for example, in my hand is moving on pricing. It still will press on the center of the control because we set the press attraction point in the center of control. So even my hand is moving. And the interaction library will adjust my hand position about the attraction point. Okay. Now this diagram shows the basic data flow to produce an interaction frame. Interaction stream is an advanced stream. They need the text data, they need the text frame and the scatter frame as its input. If we don't get if we don't put up in the text and the scatter frame, there's no interaction stream out at all. So to get an interaction frame, we need to pass a depth frame and a scattering frame first. And then the interaction stream library will calculate based on the depth and the scattering frame, and then produce an interaction frame out. Now this picture shows the components retrieved in our interaction library. Kinect interaction 170.dll implement all the core logics of our Kinect interaction library. And we have a multi-layer wrapper named Microsoft.Kinect.toolkit.interaction.dll. Based on the multi-layer wrapper, we build a control layer. So we provide several basic controls such as button, screw wheel, for the end users which can easily develop a Kinect enable app by .pl. Okay, now let's look at the Kinect interaction API. iInteraction client is an interface, which is a control writer, could implement this interface to tell our interaction library what is the attraction point and the current control status. And the interaction stream is the central class in our interaction library. We have open next frame method to get the next interaction frame. And then we have the process depth and the process skeleton method, which will allow the end user to pass in the skeleton and depth frame. Interaction frame. Interaction frame class has 6 structures of user info, 1 for each player. And in the user info, we have the hand pointers and the tracking ID for the player. And we will talk about the hand interaction hand pointer later. Okay. Basically, list all the class in our interaction library. To get an interaction frame, in our interaction stream, we have 2 modes, just as the skeleton depth stream. In input mode, we can get the next frame by call open next frame measure. Or in event mode, we can register the event handler into the interaction frame ready event. And when a new interaction frame is ready, this event will be triggered. And each interaction frame has 6 user info, 1 for each player. The user info class contains the information for one detected player, such as the skeleton tracking ID and the hand pointers. Hand pointer is a class of the interaction hand pointer class. In the interaction hand pointer class, we have the information about the hand, such as if the hand is tracked and if it is interactive. Or we also have the hand tap, or if it is pressed, such things like this. We also have the raw hand coordinate and also the adjust hand coordinate based on the attraction point. So this is 2 different. And then we already talked about it. Interaction client interface should be implemented as
I have a question on the
this one? Oh, sorry?
So you've shown the demo showing single hand interactions. Can I interact with my secondary hand as well? And so can
yes.
I do button presses, or is it only with the classic?
Yes, actually we can recognize 2 hands. But what the behavior for the 2 hands is on the control the logic, right? So some control maybe support 2 hand interaction, but some control only support 1 hand interaction. Yeah, we can handle it. Okay, this is the sequence chart about how to use the interaction measures. When a depth frame ready, we should call the process depth method. And when a skeleton frame ready, we will call the process skeleton method. And the interaction stream will calculate the interaction frame based on the depth and the skeleton frame. And the line, it will call the get interaction info at the location method, which is defined in the interaction client interface. To query from the client what is the attraction point of the control. And also, if the control is pressable or droppable or grippable, then it will produce the interaction frame and trigger the interaction frame ready event. So the client application can get a new interaction frame out. Okay. The control basics stuff here we just showed is a very useful sample to write interaction control. So, okay, I think that's all for today's tutorial. So, any questions?
I have a comment, yeah. So the interaction stuff, the way it's being shown at the end here, took a while to come together, and it didn't come out in the original SDK. So people had to write applications, and as you probably know, there were a lot of people that wrote applications, but they had to use all that low-level stuff that you saw earlier and write it from scratch. So this has significantly reduced the difficulty in building applications now. It's not the end of the story, no doubt, but it's really good to see this in. And it took quite a while, because this is harder than it looks. There was a lot of complexity to having this higher level of abstraction over the raw APIs. And I think it's to the credit of the team that we've managed to come up with a solution now that will empower developers to build applications more easily. I'm sure there's more to come, but I'm very reassured that you don't now have to use all that low-level stuff to build applications. You've got it there if you need them. You can get much more flexibility with the SDK. We've not hidden anything. You don't have to just use this. You can work at either of these two levels.
Okay. Any questions?
You said that Kinect 2.0 will rely on different technologies.
Yeah.
What do you mean?
They use even the operator on hardware devices to measure the data in the setting in the time of flight. Time of flight usually measure the time, the light to the object and reflect the processor and detect the data. So that's all a sample. In the current algorithm, so the data will feel the data is very noisy. There's some noisy on the border.
I don't see that now, but it's up.
Yeah.
The shape's very rough.
Yeah. And in the new session, it has a big improvement. So maybe we can see the improve our search in the new session. So actually, in November, the key for Xbox will be released. Maybe you can take a look.
And to account increased resolution in that sensor. I mean, because I heard some speculation about what's going to happen in the harm of the Kinect 2, and there are some people think that it would be possible to recognize finger motions. Do you think?
Actually, there's a public, sorry. The event I talked about already very public. So actually, in the public video, we can see the demo of the Kinect. We can recognize our hand now. We have 3 joints for hand, and we will have 25 joints for the push button. So we can basically recognize some basic pose for our finger, but not extreme. It's hard.
That's in the skeletal tracker that comes with the SDK, but you can write your own skeletal tracker if you have the technology, the extra resolution will come with the figures. But the tracker that was reproduced just has the, because of the distance it's the same.
Thank you very much. I just wonder what particularly the detection of skeleton is kind of amazing. And I wonder what can it mean to does it require motion or tangent?
Basically, it's a pipeline to detect skeleton. And with first one, we must have a background remove algorithm for remove our skeleton data. So to remove our failure depth from the background. And line we use some.
So you mean that it needs a kind of 3D version as well?
Yeah, we use some machine learning technology to recognize the each part of our body and give a skeleton.
So even though it's a kind of static object, you can detect the skeleton. And that doesn't move.
Right.
If the object does not move, still you can detect the skeleton.
Sorry, I'm not clear.
It doesn't require on a sequence of movements.
So
it doesn't work.
Motion of the object is not recorded.
Yes, yes.
What we make of Kinect Fusion, 3D scanning requires some motion,
Yes,
so you can see around an object. But the skeletal tracker, you can just stand in front of it and it sees your skeleton.
Yes.
Because my background, my target drops. They do not think. So they need to be this kind of instruction. So I just think that's an application.
Within the movement of the skeleton.
To recognize the skeleton of a crop, you'd have to run your own machine learning algorithm.
Yes.
Our machine learning only understands people.
What fusion something I observed, like when you scan a 3D object, it has to be slower. I mean, sometimes when you move really fast, what happens is like sort of misaligns.
Yes, yes.
So is it like a challenge with the application as such, or it's something related to the performance of the computer which I'm using in the practice of that?
Yeah, I think so that is both. Could the algorithm not be deal with a very faster move about our sensor? If we move too fast, we will not track because it has to align one by one. And also, we got a powerful CPU, a powerful machine with a powerful GPU card. Then maybe we can move our sensor a little bit faster.
How fast is your GPU? What chip do you have?
I know that it's like a very much good performance computer, but I don't exactly know what the GPU is used. But it gives a pretty good performance when we scan certain objects. The only problem, I mean, is that the internet user is basically probably or someone who's studying archaeology, sort of things like that. So, I mean, yeah, we have to tell them that you should use this slowly.
Yeah, fusion is a bit subtle, you're right. You sort of have to learn how to use it. It's a little bit sensitive.
Yes.
It's not for it's not foolproof. It's not just trivial.
It's work in progress.
Yeah, it's the leading edge. It's very grateful that the product team are risking putting this research technology, but the demand for it is very high. So we should keep pursuing it. Because it's on the bleeding edge, it also means that it improves quickly too. So it's getting better all the time, but it's still needing a very high end graphics.
Also in 1.8 release, we have a new some in the moving camera stack. So we can have 3 or 2 static cameras, and one page of object of the data on the camera, so we can scan the 3 models. Yeah. So we don't need to look at the camera or the object. Any questions?
Anyway, Wogan just said that there's just 10 minutes remaining of a tea break outside, so maybe we should close now
Yeah, sure.
and break for further discussion outside if we need, if people want to have some tea.
It's okay. Right?
Yeah, so that's great. Thank you very much, everybody, for coming. Enjoyed our presentation.